Hello and welcome again to Civil Engineering Mathematics A. This is program 7. My name is Eric Tune. I'm a lecturer in Central TAFE in Perth. Well, in this program we're going to combine aspects of programs 2 and 3 when we discuss geometry with aspects of programs 4, 5 and 6 in which we dealt with algebra. The subject is called analytical geometry or analytic geometry. We're going to study part of that. We're going to look at lines only, and then the subject is sometimes called straight line coordinate geometry. Now, a lot of applications of this subject is certainly in engineering, for instance finding the center of mass or finding a drilling angle when you want to dig for a mine shaft. In business there are applications with break-even point. So it's a very important subject. It's also a very interesting one, and one that students generally find relatively easy. So there you go. After all that heavy algebra of the last few weeks, we're now going to move to something a little bit easier. Let's have a look exactly what is covered in program 7. The first thing we're going to talk about is the Cartesian plane. Then we look at the slope and intercept of lines, followed by the actual equation of a line, and then we have a look at special formulae for lines, points of intersection. We're going to solve simultaneous equations, and lastly we have a look at what's called the line of best fit. The line of best fit is actually quite important. It can be used to make predictions, as you will see later on in the program. Cartesian plane, that's what we start with. Well, it's a clever idea. It was thought up by somebody called Cartesian, or sometimes called Descartes, to represent points in space. In two-dimensional space, it's of course just the length and the width. In three-dimensional space it becomes a little bit more difficult. To think of that first is quite an achievement. How do you represent points in space? Well, Cartesian thought of this idea of two axes at right angles to each other. Let's have a look on the screen. We've got a x-axis, the horizontal axis, and you see a number line with 1, 2 and 3, positive to the right and negative to the left, 0 in the middle, and then we've got the other axis, the y-axis at right angles to that. That point there in the middle is generally referred to as the origin. It's got coordinates 0 for x and 0 for y. So you can represent any point using these two coordinates. For instance, this point over here would have an x value of 2 and a y value of 2. And that would be written as 2, 2, an ordered pair. Let's now look at a specific example. Plot the points A, 1, 2 and B, -2, 1. Points, by the way, are always designated by capital letters. Here come the axes, x and y axis at right angles. And here's point A, which has an x of 1 and a y of 2. And the point B is on that in the other quadrant. In fact, these things are called quadrants. This is quadrant 1, quadrant 2, quadrant 3, quadrant 4. That's something useful to remember. Point B has coordinates -2, 1. So we go -2 along the x-axis and we go 1 up for the y. Now it is possible to make patterns with points, and an obvious pattern is a line. And in fact what you have to be able to do in this subject is to draw lines on these Cartesian coordinates. And here we go. Let's have a look at an example. In this problem we are asked to graph the line y equals x plus 1. What we really want is a set of ordered pairs that follow that particular rule or this equation. And you can take any values of x, but generally you would like to take values that are easily calculated. I've taken an x equals -1. That gives me -1 plus 1. It gives me a y of 0. Then you can take another point for x, 0 for instance. If you substitute that in, you get a y equals 1. And a third one, x equals 1, gives me a y equals 2. It's normally written up in what is called a table like this, an ordered pairs table. X there, y there, and there you've got the values you just found. That will appear on the next screen. And now we are ready to actually graph the line. Here we've got the axes. You put the first point down, that's the -1, 0. The next point is the 0, 1. And the third one is 1, 2. And you draw your line through it. And that's how that first line is drawn. You actually only need 2 points, but it's always good to have a third one as a check. Now this was quite a simple example. You understand, of course, that it can become a little bit more difficult. Let's get a bit more practice in, though, of this type of equation. So problem 2 coming up now. Here we have the graph y equals 2x minus 1. Same idea. I just select any x value and I take easy values for x, like 0 for instance. I substitute a 0 in and I get a y equals -1. I substitute an x equals 1 in, I get a y equals 1, and then a 2 gives me a y equals 3. Table coming up like this. Here we've got the axes, the x and the y axis. Let's put the points in. 0, -1 is over there. The next point is 1 with 1. And the last point is 2 with 3. That last point is really a check. Here goes the line. And you've drawn your graph. You've drawn the graph of the line. Now there are 2 special lines I just want to draw your attention to. They don't look like lines, or they don't look like equations of lines, but they really are. Got an example here. Graph the lines x equals 3 and y equals -2. Here we've got the axes. Now how do we graph x equals 3? Well, basically what you get is the line that has all values of x equals 3. It doesn't matter what y is. So that's this particular line over there. Because on this line all the x values are 3. It doesn't say anything about y, as I've said before. So this is it. There we've got the y-axis, by the way, and that would have equation x equals 0. Now what about y equals -2? We're looking for a line where the y values are always -2. That is this line over there. Similarly, the x-axis would actually have equation y equals 0. So there are some unusual lines there, but we come across those quite a lot. Well, we're going to have a look at the equation of a line in more detail after a break. Let's take a short break now. We are now going to have a look at the general equation of a line. There are in fact 2 things that determine a line. The first thing is what's called the gradient, the slope of a line, and the other one is where it cuts the y-axis, and that's called the y-intercept. Let's look at the graphic here. Here we've got lines that all have the same gradient, they've got the same slope. On the other hand, in this particular diagram, we've got all lines passing through the same point. Now once you know the point and you know the slope of the line, then the line is completely determined. This leads to the definition of a slope. In fact, if you look at what a slope is, then it is how high you go up when you go in a horizontal direction. And what we normally do is we take the horizontal direction to go in this positive direction, and then the ratio of the rise over this so-called run, that is then defined as the gradient. Here's the definition: gradient equals rise over run. Let me give you some examples of different gradients. In the first example, we've got a horizontal line. Well, there is no slope at all, and so therefore the gradient is 0. In the second example, the line makes an angle of 45 degrees. That means that for every unit across horizontally, you go 1 unit up. The gradient would be 1. Now this particular line hasn't got a gradient at all. In fact, we say it's undefined. We'll come back to that example a little bit later on. Then we come to the fourth example, and there we've got a very narrow negative slope, as it is called. I've approximated as 0 point or negative 0.3. It is negative because for every unit across I'm going about a third of a unit down. It's a negative slope. It's a fall, in other words. Now it is possible then, knowing the gradient and knowing where the line intercepts the y-axis, to actually get the equation of the line. The equation of the line is normally written in that format as y equals mx plus b. It's on the screen right now. Here we've got a line we normally write it as y equals mx plus b, where m is the gradient and b is the intercept. So remember that, of course, the gradient is rise over run, and the intercept is the intercept with the y-axis, where it intersects the y-axis. We'll go straight into some examples. Here we have to find the equation of that line. Now let's have a close look at it. Here we go. That particular line passes through the point 0, 0. It also passes through the point 1, 1. So for every unit across, I'm going 1 up. The gradient therefore must be equal to 1. I also know that the line passes through where y is equal to 0. So the y-intercept should be 0. In other words, the value for b must be 0. If m equals 1 and b equals 0, putting that into the equation, y equals mx plus b should give me y equals x. Now, not all problems are that easy. Let's look straight away at another problem, number 2. And here it is, problem number 2. We've got a line that passes through the point where y is equal to 1, so we can pick up there that b must be equal to 1. Now, what's going to be the slope? We expect something negative, because whenever I move 1 unit across, then I'm going down, see, with my y value. In fact, if I take these 2 particular points, then I can see that for 2 units across, I'm going down by 1. Well, that translates to a gradient of -1/2. We already knew that the b had to be 1. Put it in the formula, y equals mx plus b, and I've got the equation, y equals -1/2x plus 1. So that was quite a difficult problem. Now, there's actually a general formula available that if you have 2 points, that you can then calculate the gradient. That's where the algebra comes in very handy. Formula comes up on the screen. We've got 2 points, call them x1, y1, and the other point would be x2, y2. That's the general sort of notation you use. Now, how can we get the gradient from those 2 points? What we need is the rise. Now remember, the rise is the y displacement. We can call it y2 minus y1, the difference in y values. The run, you'll find to be the difference in the x values. So that's the x2 value, that's the x1, so the run is the difference between those 2 values. And then, of course, the gradient is the ratio of the rise over the run. In formula form, that becomes y2 minus y1 divided by x2 minus x1. Now, I warn you that in these sorts of problems with that negative, and especially if you deal with negative x and y values, that you can easily make mistakes. You have to know your algebra about directed numbers. We talked about it, of course, in program 4. Let's do an example. Find the gradient through, of the lines through -3, 7 and 2, -3. Now I can call x1 -3 and y1 7, and of course do the same for x2 and y2. Now put it in the formula, y2 minus y1 over x2 minus x1, and careful with those negatives. So I get -3, subtract 7, 2, subtract -3. Now remember that subtracting a negative number is the same as adding a positive. So we end up with -10 divided by 5, and that can be simplified to -2. Obviously, when you have 2 points, it's not only possible to determine the gradient, but to actually get the equation of the line, because there's only one line that passes through 2 points. Now, there's a particular procedure that you might want to use. In the book, they talk about another procedure, but I think this is a little bit easier. I would first obtain the gradient using that equation we just talked about earlier, and then you find the b value, the y-intercept, by substituting one of the points into the general equation for that line, y1 equals mx1 minus b, and then you write the equation as y equals mx plus b. Let's get straight into a problem. Here I've got a question: what is the equation of the lines for 2 points, 2, 5, -4, 17? First of all, get the gradient. So it's going to be y2 minus y1 divided by x2 minus x1, and that gives me this particular number, 12 over negative 6, which is of course negative 2. I know then that the gradient is negative 2. Substitute that negative 2 into the equation for a line, the gradient equation of the line, using that first point. So I've got 5 for that y value there, and I've got a 2 for the x value there, and I've got the negative 2 for the gradient. And that gives me an equation from which I easily can find b. In fact, b is going to be 5 plus 4 equals 9. I know what m is, I know what b is, and consequently I can write the equation as y equals negative 2x plus 9. Now, talking about equations, there are in fact 3 different ways of writing lines. I prefer the y equals mx plus b way, but there are other ways, and I just want you to know those because they are referred to in the book. We've got the gradient form, y equals mx plus b. Then there is something called the general form, and that's got an ax plus by plus c. Now, with the gradient form, the m and the b have particular meaning, but in the general form, the a and the b and the c do not have a meaning. So I would prefer this particular way. There is a third way, and that's called the intercept form, and that's quite interesting. Then you write the line as x over a plus y over b equals 1, and you'll find that the little a and b are respectively the x-intercept and the y-intercept. Let's do an example on that last one. Here we've got a line that passes through these two intercepts. The x-intercept is 2, so a equals 2. The y-intercept is 1, so b equals 1. We can write therefore the equation as x over 2 plus y over 1 equals 1. We can do some algebra to clean that up a little bit, writing it as y equals 1 with x over 2 transposed to the right. And we end up with y equals a half x with a negative in front, so negative a half x plus 1. This was quite an interesting way of writing a line and very useful in certain parts of mathematics. Now, we have a small break and then we come back with simultaneous equations and how to solve those graphically. You will recall that in program 6 we solved simultaneous equations, and I mentioned that it is also possible to solve simultaneous equations using graphs, and that's what we're going to do now. Each of those equations actually represents a line, and where the two lines intersect you get an x value and a y value, and those two are then the simultaneous solution to that set of equations. Let's look at an example here, easy one. Here we have to find the simultaneous solution of y equals x and y equals negative x plus 2 minus x plus 2. Set of axes, y equals x is easily drawn, of course, because that passes through the origin and the point 1, 1 and 2, 2. The other line has a negative gradient, negative 1. It passes through the point where b equals 2, and you can clearly see where they intersect. They both pass through 1, 1, and that is the simultaneous solution. So, in other words, x equals 1, y equals 1. Next problem, a little bit more difficult, and in fact here we might have to write out a table before we can draw the graph, and that's what I've done here. I've selected some x values, negative 2, 0 and 2. I've selected them so I get easy substitution. If I substitute negative 2 into that equation, I get 0 for y. I've done the same for the other x values. The table for the other equation appears here. That enables us then, of course, to draw both lines. Here we go, that's the first line, and notice that I have actually indicated on the graph what line it is. That's always a good idea. In this case, y equals a half x plus 1. The other line was y equals 2x. Take 2, have a look where they intersect, and of course if you've got accurate graph paper, that is going to be a lot easier than on this particular graph, but you can still see that they intersect at the point where x equals 2 and y equals 2. We're now having a look at some practical applications of all this material, and one of the applications is called line of best fit. What frequently happens is that you collect some information and you want to see whether two variables are related, and if they are related, by what sort of an equation. Now sometimes that relationship can be quite complicated. It can be a curvilinear relationship, or it can be an exponential relationship, a logarithmic relationship, or hopefully a linear relationship, because they're certainly the easiest to deal with, and they're the ones you can deal with because we have worked through some of the problems. Now let's have a look what is actually meant by a line of best fit. It actually is the point of the line that best represents the set of points. Here we've got a set of points. These are observations I've made on two variables, and here I've drawn a line through these points that I think best represents those points. Now once I've done that, then I can actually make some predictions. For instance, I might have a value over here on this x-axis, and I want to know what value corresponds to that on the y-axis, and I can use that line of best fit. Sometimes it's called a prediction line. So the line can be used to estimate values. Let's go into some problems like this. Here we've got the first one. We've got a line drawn over here. We've got two variables, one p and one q. Here's the line. Now the first question asks, what is the value for p when q is equal to 5? So I select the value for q equals 5. I go to the line and I see what value of p best represents that point. Let's have a look. I find from that if p equals 4, or then q is equal to 5, sorry, then p is equal to 4. I put arrows on the line to indicate what direction I'm making my estimation. In this case, I want to know what q is when the p value equals 6. So I would start with 6 and then go across horizontally, and I find from the line then that I can estimate the q value as to be between 7 and 8, about 7.5. When we conduct an experiment, the data we collect is called empirical. Now, what do we do when we have empirical data and we suspect that a line passes through a set of points? Well, you do the same thing as we've done before, except that the numbers are generally a little bit more awkward, and some of the points don't quite lie on the line. You take two appropriate points and you do the same thing. Find the gradient, find the intercept. I've got the procedure written up here. Select two appropriate points, you obtain the gradient using the same formula as before. You use one point to get the b value, and you write the equation as y equals mx plus b. Let's go straight into a problem. I've collected some information here about the mass and the length of cylinders with identical cross-sections, and I've measured them as follows. Now we suspect that the values of L and M are linearly related. In other words, that they would be of a form M equals gradient times L plus an intercept. That is the difficulty with these type of problems, that you don't always deal with x and y, but you have different variables like x and y. And here, of course, we've got an a and a b as well, a standing for gradient and b standing for the y-intercept. Okay, we select 2 points. Now I've selected the first and the last, but you can take other points. If one point is completely way off, then you should not use it. Perhaps a little sketch of the points will give you an idea if there is a value that is way out. I have checked, those points are approximately on the line. We use the formula for the gradient, difference in the y's becomes 20.7, difference in the x's 7.5. 2.76 if I divide that. Then we substitute that into the equation y1 equals mx1 plus b to get the value for b, and that comes to 0.1, which will enable us then to write the equation m equals 2.76L plus 0.1. Well, we're nearing the end of this program. I hope you found it interesting. Certainly you see how practical applications come into this work. That last problem was quite interesting. I hope you agree. Let's see what we've covered in program 7. We looked at the Cartesian plane, then we looked at the slope and intercept, followed by the equation of a line. We looked at special formulae for lines, the point of intersection, simultaneous equations, remember, and then lastly we did line of best fit. The work we have done in this program is covered in chapter 8, and you should do as many problems as you can. Please don't forget that there's a website that has additional examples, and if you're enrolled you can access that website. Well, this is the end of program 7. I'm looking forward to your company in program 8. Bye for now.